Welcome to this explainer. Okay, today we're stepping right onto the construction site of one of the absolute most fundamental and, frankly, powerful data structures in computer science. We're going on a true builder's journey into the physical mechanics of creating a linked list in C. So grab your hard hats and, your focus, because we are getting completely hands-on today. We're going to tackle memory allocation, physical linking, and craft a 3-node masterclass right from the ground up.
Section 1, Anatomy of a Node, the building blocks. Okay, let's dive into this.
Every great structure absolutely has to start with a blueprint, right? Before we look at any actual C code, we really need to understand exactly what it is we're building. So a node is our structural foundation. Don't think of it as some abstract line of code. Think of it concretely, like a literal physical box sitting out there in computer memory. Inside this box, we've got exactly two things. First, a stored value, like a number, and second, a memory address. Think of it as a physical directional sign pointing directly to where the next box is located.
Now here is our ultimate architectural goal. This is the final building we're trying to construct today. We want 3 distinct nodes holding the values 10, 20, and 30, and they need to be physically linked together in a sequence. Notice that the final node, the one holding 30, must be safely grounded. In C, we ground that last link by pointing it to null. It basically tells the computer, hey, stop, this is the absolute end of the line.
So to actually build that chain, we've got to translate our physical box analogy into C code using a struct. Our C code defines a struct node with 2 very distinct compartments. The first compartment is int data. This is simply where we hold our stored number, like 42. The second compartment is struct node star next. Now that little asterisk, that's incredibly important. It means this isn't just another number, it's a memory address. It's the signpost pointing exactly to the next physical box in our chain.
All right, now that we have our blueprint perfectly understood, it's time to actually pour the concrete. Take a look at the memory canvas here. Step 1 is setting up our environment by including standard lib.h. You have to do this. It's absolutely required because it unlocks our memory allocation tools. Step 2 is initializing our empty list. We literally just create a pointer called head and immediately and safely set it to null. So right now our list has 0 nodes. Our head pointer is pointing to nothing, meaning our list is officially empty, but it's perfectly secure.
Okay, here comes the heavy lifting. To forge the very first node, we use the malloc command. That stands for memory allocation. We're asking the system to carve out exactly enough space for one struct node. We then store this brand new space in a pointer named node1. Crucially, we immediately check if node1 equals null, because if it does, it means the allocation completely failed. But once we verify it isn't null, we place the number 10 into its data compartment, set its next pointer to null, and finally connect our head pointer to this brand new node. Boom, we are on the board.
Next up, we just repeat the process. We use a new malloc to create node 2, check it, populate it with the number 20, and set its next pointer to null. And this brilliantly illustrates the real magic of linked lists, the physical link itself. Just look at that line of code, node 1 arrow next equals node 2. By writing that one line, we are taking the directional signpost inside our first box and aiming it squarely at our second box. You can see it perfectly right there. The chain is actually forming.
Building momentum, we allocate a third node, pop a 30 in it, and link node 2's next pointer right to it. The 3-node structure is officially complete and prints out beautifully. But let's pause for a second and emphatically focus on the memory cleanup sequence. What we build in C, we must absolutely dismantle to prevent disaster. Before our program ends, we purposefully call the free function on node 3, then node 2, and then node 1. This politely gives that memory right back to the computer, and we safely reset our head back to null.
So our structure is up, but how do we actually walk the halls? I want you to think about this for a second. It's a crucial question. How do we actually traverse this chain without losing our place? I mean, if our program only keeps track of the head of the list, how do we confidently reach the very end without breaking the whole thing apart?
Well, the answer lies in the chained arrows. You can think of chained arrows exactly like a turn-by-turn GPS navigation system driving straight through computer memory. If you use head arrow data, your GPS stops at the very first node and yields 10. If you type head arrow next arrow data, the GPS drives past the first node, follows the pointer to the second node, and retrieves 20. Add one more arrow next, and your GPS navigates deep into the structure, arriving safely at the third node to find the number 30. Now, writing out node 1, node 2, and node 3 works totally fine for a tiny 3-node list, but what if you have 100 nodes? Or 1,000? The novice method collapses because you'd literally be forced to write 100 different variable names. No way! The professional method is to use a single tracking pointer, usually called current. You just set current equal to the head, then you simply update current by saying current equals current arrow next. This allows that one single pointer to hop gracefully along the chain, node by node, endlessly. It scales flawlessly to absolutely any size.
Where's all this actually happening? We really have to break down the sharp juxtaposition between the two main areas of memory, the stack and the heap. The stack is where your normal local variables go. It has a fixed size and is super safe. Variables are automatically freed when a function ends. malloc, on the other hand, places our nodes in the heap. The heap can dynamically grow and shrink, which is awesome, but it requires manual deallocation. Heap memory is persistent. It will sit globally in your system forever until it's explicitly freed.
Let's walk through this code snippet so you can see it in action. We have a function here. Inside it, the integer x is created on the stack. When that function ends, x completely vanishes. It's just gone, automatically. But right below it, our pointer n is mapped to a node created with malloc on the heap. After the function is over, that physical box is still sitting in memory. It doesn't disappear. If you don't manually call free on it, you have just created a permanent memory leak.
So, the crucial point is that you must religiously follow a pre-flight checklist before creating any node. Include standard lib.h from malloc. Use malloc properly. Always check if malloc returned null. Set your new node's next pointer to null initially to keep it safely grounded. And finally, link it properly to the previous node. I promise you, following these rules will save you literally hours of debugging.
All right, we are officially switching our hard hats from builder mode to building inspector mode. Now, what's really interesting about this slide is exactly how a memory structure collapses. Look at the wrong way on the left. You create a head node. Then you call malloc again and say head equals malloc. By overwriting the head pointer, you have instantly severed the only lifeline to the start of your list. That first node holding 5 is now orphaned and lost forever in memory. The correct way, on the right, is to always use a separate pointer, like node 2, to create new items. You have to protect your head pointer at all costs.
Time to test what we've learned. Let's rapidly review our construction from the ground up. Start. Head points to null. Step 1, we create node 1, assign it 10, and anchor head to it. Step 2, we create node 2 in total isolation and give it 20. Step 3, we take node 1's pointer and physically link it right to node 2. Steps 4 and 5, we create node 3, link node 2 into it, and ensure that the final node's pointer drops safely into null. Look at that. Every single piece forms the complete chain perfectly. I've shown you how to build it perfectly, but let's be real. In the wild, you are going to encounter broken code. So, are you ready for a challenge? Take a breath. Let's see if you can spot the memory leak. Take a good hard look at that bottom line of code. Head equals second. What exactly happens here? Well, by pointing head directly to the second node, the head pointer is completely overwritten. Because we didn't link the first node to the second node beforehand, that original first node, the one holding the value 5, is entirely disconnected. It's gone, completely lost forever in the void. You cannot access it, you cannot free it. It is a textbook, absolutely fatal memory leak. And that brings us back to the complete bug-free picture. You can see the full sequence properly linking nodes 1, 2, and 3, culminating in that perfect target architecture we started with. Notice how our final printf statement expertly uses those chained pointers to print exactly what is sitting in memory, proving our success. Just always remember the golden rule. Check that malloc return value and free absolutely everything when you're done. Thank you so much for listening to this explainer. We've successfully forged a continuous chain in memory today. But what happens when you need to delete a link directly from the middle of the list without breaking the whole chain? That is a puzzle for our next explainer.